Right. Okay, well, hello everyone again, and welcome to another online meeting of the Havering Astronomical Society. It's great to have you all with us again this evening, and as we mentioned earlier, I hope you're keeping well and been enjoying the recent warm weather. Although I think, as Emma's just mentioned, that we're in for some cloud and possibly rain over the next couple of nights, so not much in the way of observing, I think, going on for that point. But anyway, we shall see. So straight in then, our speaker this evening is Dr. Jeff Wagg. Jeff is an astronomer and currently a project scientist at the Square Kilometre Array Organisation. He's at Jodrell Bank here in the UK. Since leaving his native Canada, he's worked at a number of observatories across 4 countries, including the Mauna Kea Observatories in Hawaii, the National Radio Astronomy Observatory in New Mexico, the Large Millimeter Telescope in Mexico, and the European Southern Observatory in Chile. And I understand that when he's not involved in anything astronomy-wise, outside the office, he enjoys scuba diving, hiking, and surfing. So quite a bit of an action man. Anyway, Jeff's talk this evening is entitled A Golden Age for Radio Astronomy, where he's going to tell us about the next generation of major radio wavelength telescopes, the Square Kilometre Array. And hopefully he's going to describe to us the status of the array and its design work, and present an overview of some of the questions that the array hopefully will answer for us in the future. So without any more from me, I'll hand over to Jeff.
Great, thank you very much. Let me just see if I can get this set up here. Share, and you should now see full screen.
Yep, that's great.
Perfect. All right, great. Thank you very much. And good evening. It is a pleasure to join you all for this meeting, and I do regret that I cannot be there in person. Most of you will be very familiar with our view of the sky at optical wavelengths. So today what I want to do is show you a very different view that we have using radio telescopes, working at wavelengths of maybe a few hundred microns up to meter wavelengths. Now, as the title of my talk suggests, we are living in a golden era for radio astronomy, and this is really due to the sheer number of new and upgraded radio telescopes working around the world. And so what I want to do tonight is walk you through a few of these and then end by describing the next phase of radio astronomy, which will be the Square Kilometre Array telescopes, which will be the largest radio telescopes in the world when they are completed. Now, to begin, this view will be very familiar to most of you, especially if you have ever viewed the sky from a clear southern location. So our Milky Way galaxy has more than 100 billion stars, but that's not all our galaxy is made of. So if we ignore the mysterious dark matter, in addition to the stars, most galaxies have some amount of atomic and molecular gas, as well as dust. And so the dust typically comes in the form of silicates or graphite. Now, when we zoom into the plane of the galaxy, there does appear to be regions which are devoid of stars. Now, we know this is not true. In fact, these regions are actually being obscured by gas and dust in our own interstellar medium. And so part of the reason we want to go out and observe at longer radio wavelengths is to see what's happening in these more obscured regions. So here we see a very different view of the Milky Way galaxy. This is a view that you would have with a large radio telescope like the Lovell telescope at Jodrell Bank. This is a view of the galaxy in atomic hydrogen gas. This is obviously the most abundant atom in the universe, with 1 electron, 1 proton, and 1 neutron. Now, hydrogen has a spin flip transition, so this is an emission line which can be observed at a frequency of 1420 megahertz or 21 centimeters. And so typically this is a line we use to study hydrogen gas in both the nearby and distant universe. So you can see when you look at the image here, if you can see my pointer, there appears to be wispy hydrogen gas above and below the galactic plane. This gives us some insight into how the galaxy may have formed in the past. But most of the hydrogen gas is concentrated in this thin disk, concentrated toward the center of the Milky Way galaxy. So it turns out that the galaxy looks very different across a broad range of wavelengths, as is illustrated here. So beginning at the top, the low frequency radio continuum emission typically traces what's called radio synchrotron emission. So these are electrons spiraling in magnetic fields. And generally what you're seeing at these wavelengths are things like supernova remnants in the Milky Way. As we go to slightly shorter wavelengths, I've already mentioned the atomic hydrogen gas. And shorter still, we can see the distribution of molecular hydrogen, so the H2, which we don't observe directly. What we do is we observe a molecule called carbon monoxide, which is the second most abundant molecule after H2 itself. So what's interesting about the molecular hydrogen is that this tells us where in the galaxy the fuel for star formation actually exists. So this tells us where star formation might be happening in the future. Now, as we come down to long or shorter infrared, mid-infrared and near-infrared wavelengths, generally we're tracing populations of massive stars. And of course, the optical view, which is the most familiar to all of us, traces both starlight as well as, you see these regions which are obscured by the gas and dust, which we can only penetrate by going back and observing these regions with the longer wavelengths. Now, as we go to higher energies, X-rays, X-rays show us regions of hot gas or plasma. So for example, supernova remnants will have hot gas within them, and compact neutron stars or black holes. At the highest energy still, gamma rays trace high energy regions, which are often extremely hot phenomena, such as pulsars or regions around black holes. We know at the center of our Milky Way galaxy here, there appears to be excess gamma ray emission, and it's still not exactly clear to astronomers what this is due to. So let's zoom in on one part of the galaxy in a bit more detail and see how these different wavelengths give us very different views of, in fact, the same regions. So this is a well-known star-forming region in Orion. The Horsehead Nebula, shown here on the left, is the view that you would have with the Hubble Space Telescope at optical wavelengths. And on the right-hand side, you see a very different view that was obtained using the James Clerk Maxwell Telescope in Hawaii at a wavelength of 850 microns or 350 gigahertz. And right away, you see that within this cloud, there are in fact young stars, what we call ONB type stars, forming, and they're actually heating the gas and the dust in the surrounding interstellar medium, which is then re-radiating at longer wavelengths. So effectively, these long submillimeter wavelengths are giving us kind of an infrared view into the dust and what we call thermal dust emission in the interstellar medium, both of our own galaxy as well as others. Now, how do we study the universe at these different wavelengths? Well, from the ground, across many wavelengths, we are obstructed by the atmosphere itself. And at radio wavelengths shown here, we are fortunate to have a very large, relatively clear atmospheric window with which to study the universe. However, I would point out that we do need to contend with human-made interference. So infrastructure like radio stations or satellite TV also work at these frequencies, and so therefore we need to contend with this when we're trying to observe the universe. Now, as we go down to slightly shorter wavelengths here at the millimeter and submillimeter wavelengths, much of the absorption of the incoming radiation from space is actually due to water vapor in the atmosphere, and so therefore many of the submillimeter wavelength telescopes have actually been launched into space. Satellites such as the previous Herschel mission, which was retired very recently. The other option is to go to a high dry site like Mauna Kea in Hawaii, or the Chajnantor Plateau in the north of Chile, which is one of the best observing sites. It's a very dry, high plateau at 5,000 meters in the north of Chile. And so what I want to do now is just walk you through a few of these sites and describe some of these telescopes that operate there in a little bit more detail. So beginning with the James Clerk Maxwell Telescope, this was one of the original telescopes to be built on the 4,200 meter elevation site on Mauna Kea. This is on the Big Island of Hawaii, and it was built back in the early 1980s. So originally it was a joint venture between the United Kingdom, Canada, and the Netherlands. It's now run by an East Asian consortium, but still includes funding from the UK and Canada. So if you can see my pointer, the operations base for this telescope is here on the east side of the island in a town called Hilo, which also happens to be one of the rainiest cities in America. Every day, the clouds, as they're coming in, they accumulate against the volcanoes here, Mauna Kea and Mauna Loa. And so there, almost without fail, at 4 o'clock, it will start to rain very hard. Now, because of the Canadian connection to this telescope, I was really quite lucky to work there as a summer student back in 2000. It was an undergraduate internship where I spent 8 months working on this telescope, helping to calibrate the instruments, but also learning how to surf and scuba dive and hiking on what were previously active volcanoes. So it's really a spectacular place, and I was again very lucky to start my astronomy journey at that observatory. Now, Mauna Kea itself was formed by a volcanic eruption around 1 million years ago. It's no longer active, thankfully, but the nearby Mauna Loa, which you can just kind of see the edge of over here at the right side of the screen, is still active. It has had eruptions in the last few decades. Now, what's interesting is Mauna Kea itself is the tallest mountain in the world when measured from its base at the base of the ocean to the peak. And it's, as I've already mentioned, home to some world-class observatories due to the excellent optical seeing conditions as well as a dry atmosphere above Mauna Kea. And so I mentioned the James Clerk Maxwell Telescope. This is located over here beside the Caltech Submillimeter Observatory shown here, and the submillimeter array shown here. And this is what's called Submillimeter Valley on top of Mauna Kea. Over here you see the Subaru telescope. This is an optical infrared telescope beside Keck, the twin Keck telescopes here. This is the IRTF, or the Infrared Telescope Facility, beside the Canada, France, Hawaii telescope, which is another major optical telescope, which is mostly doing surveys right now. Beside that is Gemini, the Gemini telescope here, the UCERT telescope, and the Hawaii 88-inch telescope shown here on the far end. Now, the next major large telescope project is called the 30-meter telescope, or the TMT. Many of you will have heard this is currently on hold due to ongoing disputes with the Native Hawaiians, who are the traditional owners of Mauna Kea. The land here is sacred to them, and I think there has been a long-standing agreement to host the telescopes at this site. It's a very complex issue, and I won't go into it here today, but I think it's an important lesson for all big astronomy projects that we need to respect the local traditions of the land where we're building our observatories, and also ensure very good local stakeholder engagement right from the beginning of a project. So also on Mauna Kea is this telescope shown here. This is a submillimeter array. This is a joint venture between the Smithsonian Harvard Astrophysical Observatory in the US and an institute called Asia A in Taiwan. So the submillimeter array works at frequencies of roughly 180 gigahertz up to 900 gigahertz. And this is actually an interferometer. So very different than the JCMT, which is a single dish. These interferometers effectively synthesize a higher angular resolution instrument by having these antennas placed further apart. And so depending on your scientific objective, you would move these antennas either further apart for higher angular resolution or closer together if you wanted to synthesize something that was closer to a single dish telescope. The signals from these antennas are then combined in what's called a correlator before the data are created or turned into your astronomical images. Now, the submillimeter array has really been a fantastic telescope over the years. It's shed new light into the formation of planets, as well as studying some of the most distant galaxies in the universe. Now, one thing you will notice here is that on the picture on the right, the submillimeter array is surrounded by snow, which is not infrequent, especially in the wintertime on Mauna Kea. And my first reaction is to think, well, how is there snow in Hawaii? Well, it turns out the Big Island actually has about 10 different climatic zones. And I mentioned earlier that Hilo, here on the east side of the island, is one of the rainiest cities in America. On the west side of the island, you have almost dry, arid, desert-like conditions. And this is contrasted by the tundra-like climate on the top of Mauna Kea itself. And so one can even see snowboarders and skiers up on Mauna Kea, although I would not recommend this due to health and safety considerations. The telescope operators who work on the site have in the past been called upon to rescue tourists who are injured as they are playing in the snow on the mountain. Now, this is a national park. So everyone is free to visit the observatories. Although if you ever decide to do so, I would recommend taking one of the guided tours. It's a great way to see the sunset and the observatories at the same time in a safe fashion. So from here, I want to go further east. I want to go to mainland North America, to Mexico, the site of the Large Millimeter Telescope, or what's called in Spanish the Gran Telescopio Milimétrico, which is located on another extinct volcano called La Sierra Negra. So this is at an elevation of 4,600 meters, and the observing conditions are actually quite good. So the diameter of the telescope here is about 50 meters, making it one of the largest single dish telescopes in the world. The guy here in the top right is a guy named David Hughes, who is has been the director of the LMT now for about 10 years. He was also my PhD supervisor, and interestingly, he's from the UK and did his PhD at the University of Central Lancashire, just north of where I am in Manchester. Now, the LMT itself is a partnership between Mexico and the University of Massachusetts in Amherst, with support from the National Science Foundation. And then some funding has recently been contributed by the Spanish astronomy community. Now, here are some images showing the construction of the LMT, which began in 1998. I arrived as a PhD student back in, I think, 2002, and graduated in 2006 when the LMT was being inaugurated. Now, here in the bottom left-hand corner, you can see one of the 1,420 panels which make up the surface of the dish. These are made of nickel, or a nickel rhodium composite. Now these panels sit on actuators, and the reason for this is that with these large single dishes, often as you're tracking sources across the sky, due to the effects of gravity as well as the differential heating by the sun, again throughout the day, you'll get deformations of these dishes. And this is compensated for, in this case, by what's called a primary active surface. So effectively, you can move these panels on these actuators to make up for the fact that the dish is effectively deforming as you track sources across the sky. Now, just let me quickly show you here a little video. This was a video taken from a drone above La Sierra Negra, showing you the LMT in a bit more detail. Now, one thing that's quite interesting is if you look at the surface of this dish, you'll see that it appears to be made of two different types of panels. And this is indeed the case. In fact, partway through the project, they ran out of money to complete the surface. And so what they decided to do was actually start using this telescope with only a 32-meter diameter surface. And so you could still make successful scientific observations this way. And what they did is to produce scientific results with that reduced scope instrument in order to justify the funding to complete construction of the telescope. And now you see it is fully operational. It has been producing great scientific results as a 50-meter diameter dish. Okay, so now I want to move further south from the LMT into Chile, which is home of the Atacama Large Millimeter Submillimeter Array, which is actually the largest submillimeter wavelength interferometer in the world. It's a joint collaboration between the European Southern Observatory, whose headquarters is in Garching, Germany, the National Radio Astronomy Observatory in the United States, and the National Astronomical Observatory of Japan. And again, it's hosted by Chile, in the site in the north of the country, which is considered to be one of the best sites in the world for these submillimeter wavelength observing. Now, the telescope itself is comprised of 66 of these 12 and 7-meter diameter dishes, shown here in the top right. The elevation of the site is about 5,000 meters, and that's one of the reasons it's such an excellent site for the submillimeter wavelength science. So there are 10 frequency bands covering 31 to 950 gigahertz on the ALMA telescope. And as an interferometer, you can change the separation between the antennas, again, for increasing or decreasing the angular resolution. to a maximum separation of up to 16 kilometers. And this is one of the reasons why they chose this site. It's a very large plateau at a very high elevation. Now, what I want to do is just show you, this is a promotional video put together by the ALMA group. And what I'm doing here is I'm going to walk you through the site and show you some of the characteristics that make it such a great site. So again, it's at 5,000 meters. There are volcanoes in the area. Most of these are inactive, so they're not a high risk to the project itself. But it is one of the highest astronomical sites in the world. If you're interested in seeing the sky at optical wavelengths, it's one of the clearest views of the heavens that I've ever seen. There's a little village called San Pedro de Atacama where you can visit and see the sky, as well as visit some of the indigenous communities. The conditions can be quite harsh. You will get strong winds. You will get hail even at this high elevation site. So you can see here a combination of these 12 and 7-meter diameter dishes. Now, the dishes typically observe the same objects in the sky, and again, the data are combined before an image is created in an instrument called the correlator. So one thing you can see here at the bottom of the screen, and here as well, are these little pads. So effectively, these antennas can be moved from one pad to another, depending on the scientific objective of your experiment. Now, when we observe at submillimeter wavelengths, we often talk about observing the cool universe. So again, these are often objects you can't see with your optical or infrared wavelength telescopes. And so we're typically observing gas and dust at temperatures of a few tens of Kelvin. Now, I showed you earlier a star formation region in Orion. So ALMA has been doing some fantastic scientific observations of star formation regions like this. Here are a pair of binary stars in the process of formation. We can also study how planets form. So this is an image of a disk around a nearby star where it's believed that there are planets forming gaps in these rings around the star. Here's an image of the molecular gas around two galaxies which are in the process of interacting. And we can also look for big molecules in the interstellar medium, prebiotic molecules which would have given rise to life like we see on the planet Earth. Now, again, the conditions can be very harsh, but they're also, because of the high elevation, the engineers and technicians who work at this elevation often require supplementary oxygen to be able to concentrate. Imagine this computer, which is the computer that combines the signal from the antennas or the correlator, is at the high elevation site. And so the engineers who are working on this need extra oxygen to be able to focus. This is one of the two transporters that is used to transport the antennas across the different sites and laying them on the pads with millimetric precision. So as I've already mentioned, this is a joint collaboration, and as we are now with these major observatories like ALMA, we really need collaboration on a global scale in order to achieve these ventures. It's complicated, but that's part of what makes it really exciting. Okay, so what I've done now is I've shown you a few of the submillimeter and millimeter wavelength telescopes that have been used to study the cool universe. Now I want to talk about some of the SKA-related telescopes that work at longer wavelengths. Many of these we often refer to as pathfinders for the Square Kilometre Array, or the SKA. So beginning here on the top left, the Very Large Array is an array which will likely be familiar to many of you. This is an array which appeared in the movie Contact. It consists of these 27 dishes, which are located in the plains of San Agustin in the north of New Mexico. They operate between 350 megahertz up to 50 gigahertz. Now, something that a lot of people are not aware of with the Very Large Array is that since it began operations in the early 80s, it has been one of the highest impact scientific instruments operating in the ground of all time. It's really been an incredible and made incredible contributions to the field of radio astronomy. And now here on the top right, you see an experiment called CHIME. It's a kind of a funny design. It's got these parabolic dishes. There are 4 of them. And the reason that this design, I should say it's located in the province of British Columbia in the west of Canada. Now, part of the reason that this design was selected is that it gives it a very wide field of view, and it's oriented such that it's a transit telescope seeing the same regions of the sky every day. And so this makes it a very good survey instrument, and has found now more than 500 of these objects called fast radio bursts. Some of you may have heard of these. They're very short-lived bursts of radio energy, which we believe are mostly located outside of the galaxy, but they're still very poorly understood, as they've only been known about now for about roughly a decade. A really cool, huge new telescope, which has been built in the south of China in the province of Guizhou, is FAST. FAST is 500 meters in diameter. You'll notice that FAST is located or surrounded by these very small mountains. Part of the reason for that is it provides shielding from the surrounding radio frequency interference. So obviously, there are major cities which are in close proximity, and having this kind of terrain around FAST shields it from that interference that we would have to contend with when observing the universe. Now, FAST itself is so large that you cannot move the primary telescope to observe different parts of the sky. What you do is you move the secondary reflector, which is hanging from cables, hanging from these poles or towers surrounding FAST itself. Some of you would have seen the unfortunate demise of the Arecibo telescope, which happened, I guess it was later last year. FAST has got a similar design, but is much larger in aperture. Now, the kind of images that you can make with radio interferometers, such as the Very Large Array, are these beautiful images covering a broad range of angular scales in the sky of big radio galaxies such as Cygnus A. So the emission that you see here is all synchrotron emission. So again, electrons spiraling in magnetic fields. There's a very bright source at the center of the galaxy. This is, we believe, associated with a supermassive black hole, maybe 10 million times the mass of the sun. There are these jets of radio emission, which are going out the poles of this source in the center, and end in these giant, really beautiful radio lobes, which could extend out beyond the extent of a galaxy and even into the surrounding intergalactic medium. So telescopes like the Very Large Array and soon the Square Kilometre Array provide us with exquisite views of the radio astronomy universe, the long wavelength universe, such as the one shown here. So what I'm going to do now is describe to you the Square Kilometre Array in a bit more detail, beginning with this slide. And there are a lot of technical details on it, but what we're effectively aiming to build are two of the largest radio telescopes in the world, beginning with SK1-LOW in Western Australia, which will consist of 131,000 of these low frequency dipole antennas. I'll show you these in a bit more detail here in a few slides, as well as SK1-MID, which will consist of 133 dishes that I will again show you in a couple of slides, plus the Meerkat array, which is already in operation at the Karoo site in South Africa. And the plan is to begin construction activities of these two telescopes during the second half of this year. Now, the SK1 telescopes will be built and operated by an international community under the umbrella of what's called the SKA Observatory. This is an intergovernmental organization, or an IGO. So for those of you who are familiar with ESO, this will be the radio astronomy version of the European Southern Observatory. So I think it's important to point out these big mega science projects can only be achieved through this kind of global collaboration. We have more than 15 countries which have been involved in the SK, which will help fund it, as well as more than 1,000 members of our scientific community. So part of my role is to engage with that broader scientific community. And we have, again, more than 1,000 scientists from around the world who would like to use these telescopes. Now, we originally started as a small company, a private company in the United Kingdom. And earlier this year, we transitioned into this intergovernmental organization structure, which is governed by treaty. And this gives us the ability to function across the three host countries. So we have the main office in Jodrell Bank. I'll show you this on the next slide, as well as the two host countries in South Africa and Australia. And so this gives us, again, the ability to function there, but also to hire staff from the different member countries to work across these 3 sites. Now, I mentioned the main office is in Jodrell Bank. I think many of you will have had the opportunity to visit this site just south of Manchester, which is the site of the Lovell telescope shown here on the left. It was named after Sir Bernard Lovell, who is considered to be the first professor of radio astronomy. Now, currently, we have more than 100 international staff, as well as UK and international staff, who are working for this main office shown here. Over the last year and a half, the majority of us have been working remotely, although staff are starting to return now in a controlled way to working in the office. Now, I'm going to show you this video is a little bit older. It's very hard for us to take drone footage on top of the site because of the interference that these drones create with the Lovell itself. So we can only do this very occasionally. But what you see here is an image of the main office as it was being constructed a little bit more than 2 years ago now. So this was our original office, this T-shaped building in the south, and then the new office is shown here, and including this really nice council chamber where we host international science events. Just one more quick flyby here again. The parking lot is now where these big crates are, and there is a pond, but it's actually here in the middle. So this is now a UNESCO World Heritage Site, and the visitor center, which is up here, I believe has now reopened for anyone who's interested, although you do need to make reservations in advance again because of the restrictions of the pandemic. Okay, so this is one of our 3 main sites. Now I want to quickly show you the other 2 sites, beginning with the Karoo Radio Astronomy Reserve in South Africa. Now this is a legally protected radio quiet site. It's about 500 kilometers across. It's currently the site of the Meerkat telescope, which I'll show you on the next slide, and will be the place where we will build SKA1-MID, which will be our mid to high frequency array of dishes. Now, the data itself, even though the telescopes will operate here, the data would be transported to Cape Town, where the images would be created at the South African Science Operations and Data Processing Center. So I mentioned that Meerkat is a South African-led project, which is already in operation at the Karoo site. These are the 64 Meerkat dishes shown here. Because of the way these interferometers work, we can incorporate Meerkat into the SK1-MID array towards the end of construction. So then we'll have 133 plus these 64 mid to high frequency array dishes. Now, Meerkat has been operating for a few years now and has already created some really spectacular images, including the image shown here of the galactic center. What you see here is a frequency, an image at a frequency of roughly 1 gigahertz. And this spectacular image includes, for example, supernova remnants over here. You're seeing radiosynchrotron emissions, so again, electron spiraling in magnetic fields. You also see these really bizarre, previously known, although never seen with such fine detail, these magnetic field lines above and below the plane of the galaxy. And it's still not exactly clear what gave rise to these. But this is really, it's fascinating that we're still learning so much, even about our own galaxy in which we live. Now, the Meerkat dishes will be combined with 133 of these new 15-meter diameter SK1 dishes. This is the first prototype for SK1-MID. It's been designed by a group led by our colleagues in China. It's a company called SETSI54. So this is in fact just outside of Beijing, which has been designed and built in collaboration with our colleagues in Italy, Germany, as well as South Africa, the SKA South African group. You can see that the surface itself has these adjustable panels. This is a secondary reflector here, and the receivers will be mounted on this feed indexer here at the bottom of the dish. And these dishes were designed to be very inexpensive based on the frequencies at which they will observe. So I'm going to go to the other side of the world now. This is the Murchison Radio Astronomy Observatory in Western Australia, which will be the site of the second SK1 telescope called SK1 Low. This is, again, a radio protected or radio quiet site. It's about 350 kilometers northeast of this mining town, Geraldton. Perth is down here to the south. One of the things that makes it such a great radio astronomy site is that it's got a very low population density. There's something like 30 sheep or cattle stations and a population density of roughly 2 millipersons per square kilometer. And so for this reason, there isn't a lot of locally made interference. Now, the traditional owners of the land are the Wajari Yamaji people who have permitted the Square Kilometre Array project to use this land under an indigenous land use agreement. Now, already in operation at this site, again, the Murchison Radio Observatory, is this telescope here called ASKAP, which we refer to as a precursor, or again, a pathfinder for the Square Kilometre Array, because it's operating with some of the technologies that we will use for the SKA. ASKAP has the advantage that it's able to map out wide areas of the sky very quickly. So for example, this image here of the Small Magellanic Cloud was made using the ASKAP telescope by combining this interferometric data with single dish data from the Parkes telescope in Eastern Australia. So some really fantastic, very large field of view images, which are very detailed. And again, this is the hydrogen gas within the Small Magellanic Cloud. Now, also at this site is what's called the Murchison Wide Field Array. This is a low frequency pathfinder for the SKA. The MWA, or the Murchison Wide Field Array, is shown here on the top, and it's composed of these tiles of low frequency dipole antennas. These work at frequencies of around 100 to 200 megahertz. Now, the way these work is effectively a signal is made by combining the data from each of these dipoles into one, so it acts as one and almost like an antenna. And you then combine the signals from these groups or tiles of stations or antennas at the correlator before you can make your astronomical images. Now, just south of the MWA is what's called AVS1, or Aperture Array Verification System 1, which is actually a full prototype station of SK1 low antennas. So each one of these little circles you see here is actually an antenna. When you zoom in, you see that these antennas are they look very much like a Christmas tree. In fact, these are what are called log periodic antennas that have been designed to work very well between about 50 and 350 megahertz. Now, each one of these stations will consist of 256 of these antennas. And if you can imagine it, there will be 512 of these stations spread out over 65 kilometers of the Western Australia site. So this is going to be something that's really will be incredible to see when construction is completed. Now, in both the case of SK1-MID and SK1-low, the data would be correlated, so the signals are combined in what's called a central signal processor or a correlator. The data volumes we're dealing with are much, much larger than any previous radio astronomy observatory. So, you know, if I'm observing right now with a very large array, I can analyze these data and make images on my laptop or local server. With the SK, we won't be able to do that. In fact, what we're going to have are these supercomputing HPC centers in Perth and Cape Town, which will be host to what are called our science data processors. These will actually create the data cubes, or the images that the scientists will then use for their research. Now, after the science data processors, the data will be transported around the world, and the actual user will interface through a series of what are called regional centers. And this is a new concept in the radio astronomy sphere, and so we're still working on some of the details about how this will work in practice. But again, because we need to get the data to so many users in different parts of the world, from North America to Europe to East Asia, we have to come up with new ways for the users to interface with these telescopes. Now, just in the last few minutes, what I want to do is talk you through some of the interesting scientific objectives we hope to achieve with the SK telescopes, beginning with studying gravity using these objects known as pulsars. And so many of you will know that pulsars are neutron stars, which are effectively acting as cosmic lighthouses in the Milky Way galaxy. So they have very strong magnetic fields That gives rise to radio synchrotron emission. These things are often spinning at rates of maybe 1,000 times per second or once every 10 seconds, meaning that radio emission beams towards us here on the Earth. Now, one of the cool things about that is that some of these can act as very precise astrophysical clocks. And so if you have these big gravitational waves passing by, and we know now from LIGO that these gravitational waves exist, then we should see the signal of those gravitational waves in the arrival times of the pulses from these pulsars as they pass by. And this is illustrated somewhat by this image here on the right. And so again, we'll be able to test our theory of general relativity, and some of our scientists will hopefully be awarded Nobel Prizes for the discoveries that they will make in this particular field. Now we also want to understand how galaxies form. And so I've mentioned the 21 centimeter hydrogen line, which is used to study galaxies. And so, for example, telescopes like the Very Large Array will make images like the one here shown here in the middle, or the one shown here on the far right. Our computer simulations tell us that this is only the tip of the iceberg, so that as galaxies continue to form, even in the relatively local universe, we should, through very sensitive or very deep observations, pick up some of these smaller satellites, which are streaming out of the surrounding intergalactic medium. And so I think this would be a really fascinating way to view galaxy formation as it continues to happen in the relatively nearby universe. And when I say nearby, I mean distances of about 10 megaparsecs or less. Now, one of the strengths of the telescopes that we're building is that they will be able to map out very wide fields of the sky rather quickly. And so this will allow us to test our current models for how structure and galaxy formation has taken place since the time of the Big Bang, roughly 13.8 billion years ago. And what I mean by these models, this is a simulation shown here of a hydrodynamic an n-body simulation for the large-scale distribution of galaxies as it is predicted to look by these computer models. Now, what we expect to see, and you often hear this referred to as the cosmic web, is that galaxies through the pull of gravity will begin to cluster in these large clusters of galaxies, smaller groups of galaxies, which are then connected by these sheets and filaments and separated by these large voids. And so this is what the models or the simulations tell us, but we actually want to go out and test whether or not these models are correct. And so one way we can do that is to map out thousands, if not tens of thousands of square degrees of the sky and look at the distribution of galaxies and compare that to what these models are predicting. So again, this is something we would like to do through surveys with the SKA telescopes. And finally, we'd like to understand what happened in the first billion years after the Big Bang. Now, there's a period referred to as the cosmic dark ages, which would have happened right after the Big Bang, and this is a time when very few stars, very, very few galaxies would have existed. So it's very difficult to study this period directly. However, as we emerge from the dark ages into what's called the cosmic dawn, and eventually the epoch of reionization, we can start to see the first galaxies, but we can also start to study the hydrogen gas, the atomic hydrogen gas, between these galaxies in order to see how this structure is evolving and how these galaxies are impacting the gas or ionizing the gas in the surrounding intergalactic medium. So we think that the first stars and galaxies would have emitted strong photons as well as X-ray emission, which would have kicked off these electrons from the hydrogen atoms between the galaxies. And so that the universe began to ionize in this sort of Swiss cheese-like fashion. And so you would have seen these bubbles of ionized emission emerging around these galaxies until the time roughly 1 billion years after the Big Bang, when the universe was almost 99% ionized. And so our deepest observations with the Hubble Space Telescope have shown us some of the galaxies and AGN or quasars at this time, but we want to understand what was happening earlier than that. And one way we can do that is through observing the hydrogen gas at very low frequencies using Square Kilometre Array phase 1 low. So some very exciting things we have to look forward to, and I hope you would agree that, again, given the wealth of really fantastic facilities which have come online and are coming online in the years ahead, so we are in a very exciting time for this field. And it really is a really fun time to be working as a radio astronomer. And so we have this website, which I think has got a lot of really interesting material on it, but we are upgrading this now that we've transitioned into this intergovernmental organization. And so if you have any questions about the project itself, please feel free to write myself or have a look at our websites. We've got some really good material on there. So thank you everyone for your time tonight.
Just go and mute you. That's
Yeah, sorry.
Nice to see you all again.
Yeah, there was me, sort of rookie mistake. Thanks, Les. I was just saying, absolutely fascinating talk, Jeff, and a wonderful tour through your experiences with radio astronomy and taking us through what's actually going on across the globe, and with some wonderful developments. So thanks very much. And everybody did applause. I'm sure they did.
That's great. Thank you.
Right. Les, I think we've got time for some questions. Do you want me to go through them, or would you like to?
yeah, by all means, if you would, Les, you can go through them.
Okie doke. You okay to hang around for a little while, Jeff?
Absolutely.
Perfect. Okay. Well, we've got quite a few here, so let's just see how many we can get through in the time that we've got. Okay. One from Emma. Do astronomers believe the excess gamma rays are connected to black holes in the Milky Way? But if so, why are they spread out in the center of the Milky Way from your image and not concentrated around the black hole they think is in the center? Or are they from any previous collisions the Milky Way has done with other galaxies?
Yeah, it's a good question. I think that the theories I've heard put forward is it could be something to do with dark matter annihilation. That's one, and then the other is something to do with the black holes. But I'm not an expert in this particular field, but it is I think it's a very interesting question.
Right. Okay. What's the benefit of moving interferometer dishes closer together? What sort of objects would be targeted in this way rather than, say, with a single larger dish?
Yeah, that's a very good question. So if so in the case of SK1-MID, and actually as in the case of SK1-low as well, we will have a very compact core. And so this makes it very good for surveying for pulsars. So pulsars could be surveyed for with a big single dish, but you can get a faster mapping speed if you form beams across a more compact interferometer array. So this is one of the advantages, but as you've seen FAST, so FAST itself is really one of the fastest telescopes for searching for pulsars. It was very similar to the X-Arecibo telescope in that respect. The only thing is because you have a limited sky coverage because you've got this secondary reflector hanging from these cables above the dish, so you can't track significant fractions of the sky for a long period of time. If you can imagine the way this would work. It's also rather slow. You've got these cables going back and forth like this, so it doesn't have the same flexibility or speed that you would have with an interferometer with these dishes that can move very quickly and form beams very quickly.
Okay, great. And yeah, we saw those big trucks sort of manipulating those. So they're actually physically moved around on those big trucks, are they?
So there are two of those transporters, and they can actually lay down the antennas with millimetric precision on these pads, which is incredible. Now with the SK, we will not have the ability to change the positions of our antennas. We did this as a cost-saving measure, so we just lay them down once. ALMA, as you can imagine, is a very so the maximum separation between antennas is 16 kilometers, and doing any sort of cabling, trenching, or road work at 5,000 meters elevation is both expensive and can be complicated. I mean, I shouldn't say it, but I've seen situations where people were digging trenches and they actually cut through fiber optic cables that were connecting the pads. And it's not the fault of the people who do this. It's just you're at 5,000 meters elevation, so your oxygen levels are low, and it's really difficult to concentrate at these high sites.
Yeah, yeah, yeah. We have JCB problems digging up fiber cables at much
The
lower.
internet goes down, yeah.
Right. A close. This one's from Andrew. Close spacing will give a more simple pattern without possibly confusing the peaks and troughs. So could closer spaced array have wider usable bandwidth?
I'm not sure. I don't know if it affects the bandwidth. One thing is that the closer you move the antennas together, the more shadowing you have. And so, for example, if you have your antennas too close together, when you're tracking a source across the sky, you start to see the back of the other antenna. So this actually having them too close together can limit your sky coverage. It's actually an issue for the aperture arrays. So the way those low frequency antennas work is that you can only basically see about plus or minus 45 degrees from zenith. Because if you go too low below that, then you really are starting to see not only the back of the other antennas, but you get electromagnetic interference between these antennas as you're trying to track sources across the sky. So it is a bit limited, but the best way to go to observing at these lower frequencies is by using the antenna design. People have tried dishes, and it does work, but the antennas are optimal.
Okay, great. What sort of measurement or exposure times are involved to get some of the images that you've shown?
Yeah, that's a very good question. So typically, some of the images I would have shown might be 300 hours observing one part of the sky. But there are, because of the sizes of some of these science teams, there are surveys that they would like to do, which would take up many thousands or even 10,000 hours of observing time over several years. And that's to map out these very wide areas of the sky. It's different than ALMA, the telescope I showed you in Chile. Typically, the observing time requests on ALMA are about 10 hours. And it just so happens that the frequency at which ALMA is observing and its sensitivity makes it not a great survey instrument, but a very good instrument for sort of short exposures toward interesting objects like those disks with the planets forming around them, or maybe a very high redshift or distant galaxy. Whereas the SK will have a very wide simultaneous field of view, so it's more suited for these wide field surveys.
Okay, great. And if I may just ask a supplementary on that one, with the analogy with optical, where and some of us are images, we look for sort of ideally longer exposures to help with the signal to noise ratio. Is the same thing apply in that sense?
Yes, yeah. So basically, yeah, you're getting in our case, a lot of the noise will come from the electronics. Well, I guess it's similar to I guess it would be CCD readout noise in the case of optical. But we also have other forms of interference, like radio frequency interference from the satellite transmissions. And so the longer we observe, the easier it is to, there's a sort of a Gaussian process which reduces the noise down to a much lower level. We also have the ability, well, very often, most radio astronomy observatories will write these advanced algorithms which are very good at picking out the interference because, for example, an airplane generated signal will be very well behaved in time and frequency. So it's usually easier to spot, but in some cases we just have to wipe out entire frequency bands because of often it's due to satellite interference.
Great. Okay. That array in South Africa, Karoo, why the spiral galaxy-like configuration?
Yeah, so the idea there is you're effectively sampling, so you're sampling different wave modes in the objects you're looking at. So you're sampling different frequency scales, and so with patterns like that, it gives you much better sampling of what we call the UV distribution, which is effectively the combination of all these different wave modes in the sky over a shorter period of time. There is another more practical reason for having that particular structure, and that's that when you're working in these very remote locations, the infrastructure is typically your most expensive part. So roads, cables, and then of course power. And And so you want to do it in a way that is as efficient as possible. So, ideally we would say, okay, if we didn't need to worry about roads and we didn't need to worry about electricity and fiber optic cables, we would just put the antennas, have them distributed sort of in a logarithmically decreasing fashion, but have them in a more random locations, so that when we observe the sky, we would be able to sample those wave modes in the images in a much more sort of effective or efficient manner. But again, because of the need for roads and the need for electricity and cabling, they tend to adopt these more spiral patterns.
Okay. Okay. As many man-made machines now create interference for radio astronomy, are there strict protocols of use for the things like the internet on these sites?
Yes. So generally, staff who are working on the sites will be restricted from using cell phones, internet. Everything will have to be Ethernet based. And then the site itself is a legally protected radio quiet site. So for example, one of the flight paths in South Africa goes very close. So the Johannesburg, Cape Town, and reverse path goes very close to the site of the Karoo Radio Astronomy Reserve. So they've actually made a deal with the government whereby that flight path has been moved a little bit, so the airplanes create less interference. And so that's part of the deal that was made with the South Africans when they agreed to put the telescopes there, is that they have this radio protected site, and so we can't have new satellite transmitters operating or built on the particular reserve.
Okay. Okay, time for a couple of more, unless anybody wants to type a quick question whilst we're talking. What can we learn from combining radio astronomy observations with optical? And have there been any interesting discoveries that wouldn't have been discovered with just single observations?
Yeah, absolutely. So I guess, yeah, sorry, I don't have my slides up anymore, but like I was showing at the beginning, if you look at some of these star formation regions in the Milky Way, you can't tell that there's actually star formation taking place in these clouds without going to these longer wavelengths. And so there have been a lot of interesting discoveries. The pulsars would never have been discovered if it were not for the radio wavelengths. Something that a lot of people don't realize is that the first exoplanet was discovered at radio wavelengths. And so this was done by measuring the orbit of a pulsar around an unseen object. And it turned out that the object around the pulsar itself, it turned out that this pulsar was in orbit around a planet, an exoplanet. And so the guy who made this discovery was not awarded the Nobel Prize. So the Nobel Prize that was awarded recently for these exoplanets was awarded to the discovery that was made at optical wavelengths. And so previous to that, there had been a known exoplanet, but it was, I guess, maybe there's a radio astronomy an optical bias in some of the awards that are given. I don't know. But certainly by combining the two wavelengths. And another good example is that there are galaxies in the very distant universe, a very high redshift, that are so dusty, you can't see them with your optical wavelength telescopes because the dust absorbs all the emission from the galaxy itself. So for example, there's a very important class of object called submillimeter galaxies, which are these very dusty, huge starburst galaxies, which are forming stars at maybe 1,000 times the mass of the sun every year, which were only discovered by doing these surveys with submillimeter wavelength telescopes. We would never have seen them if we had used our optical wavelength telescopes to begin with. So it's really important that we combine all of these wavelengths together.
Oh, fascinating. Okay, and what looks like the final question here, do you see further projects like EHT integrating several of these arrays, and what sort of targets are they likely to be used for?
Yeah, absolutely. So we will have what's called very long baseline interferometry capabilities with the SK. So effectively what you do is you would take, say, SKA1-MID in South Africa and make one phased antenna with that you can then correlate with antennas which are spread out throughout the African continent. There's what's called the African VLBI network. And so these are old satellite communication dishes which have been converted to radio astronomy telescopes that are being used, well, twofold. One, for very long baseline interferometry, but also to help develop radio astronomy and expertise in some of the countries like Madagascar, Botswana, Mauritius, so that in the future, in future versions or future upgrades to the SKA telescopes, these countries can participate as members.
Excellent, excellent. One more, a couple more actually. If you're okay for time, Jeff?
Sure, yeah.
Yeah, okay, perfect. Would radio observatories be affected by solar storms and other types of space weather, or other types of weather, I guess, terrestrial weather even?
So yeah, so one of the things we have to contend with at the lowest frequencies is the ionosphere. So the ionosphere is it's an interesting source scientifically, but it's also something that creates extra. It's almost like looking at the universe through the bottom of a swimming pool. Like at radio wavelengths, your sources will sort of move around like this. And so we have to do these special calibration and imaging techniques, direction-dependent calibration techniques, when we make our radio astronomy images at frequencies below about 500 megahertz. And so that is, it's not a constant effect. It comes in waves. These ionospheric patches move across the Earth. And so that is something we have to contend with. So that's one area of science. There is a big area of radio astronomy solar observations that are studying, like, the surface of the sun in greater detail. And this is quite a fascinating area for the SK1 low telescope in the future.
Okay. And is there any collaboration between SKA and the Event Horizon telescope that we were just talking about?
Not formally. We actually had the director of the what's called JIVE in the Netherlands, who was one of the ones who made that beautiful image of the galactic, sorry, not the galactic center, the M87 black hole with the Event Horizon telescope, and he came to give a talk. And there are a lot of there will be scientific collaborations, like for example, observing active galactic nuclei. We wouldn't have the same angular resolution that they have because the Event Horizon telescope is working at higher frequencies. But there are collaborations naturally between the science as well as the different institutes. And so this is something where he was coming to give an update or a presentation, and we tried to get him to tell us whether there was an image of the galactic center black hole forthcoming, and he wouldn't say.
Oh well. Press him harder next time. Excellent. Right. Well, that's the last of the questions that have come up in the chat.
Okay. Well, thanks for all the great questions.
No, absolutely, and thanks for staying on and giving the great answers to those questions, Jeff. Been really illuminating. Les, I don't know if I just hand back to you for a final sort of word of thanks.
Yeah, by all means. Okay. Yeah, thanks very much for a very fascinating and interesting talk there, Jeff. It just makes me wonder what things we're going to be coming across in the next decade from the array that we have no ideas about now. And it's just going to be worth waiting to see, I think. So thanks very much for that talk. And thanks very much for your time. We now normally continue with basically some in-house notices and general chit-chat, whatever. You're quite welcome to stay and listen to any point, but if you have other plans, whatever, that's quite understandable. So thank you very much for your contribution this evening.
Okay, well, thank you very much. It was great to meet you all, and hopefully sometime in the future I'll see you all in person. We'll recognize that we all have legs somewhere underneath our heads after all these Zoom meetings. But yeah, it was fantastic to meet you all, and I hope we do get a chance to meet in person at a future event. And thank you very much for this invitation.
Yeah, look forward to it. Thank you.
Thanks, Jeff.
All right,
Thanks,
good night,
Jeff.
everyone.
Perfect. Thank you very much.